Okay, so last time we basically went down and we were here, right? Hello world. Print hello world. And what that is, well, that's a program. It's a very simple program. It uses what we call the print function. Print, we call it a function, that takes an argument. There, it's hello world. It's the string hello world. String is a fancy way to say words. And if you want to create words, like sentences or whatever, you need to put it in quotes. And so we put the string hello world. If I try to do it without quotes, it's not going to know what's going on. It's going to say, I don't know what hello is, I don't know what world is, invalid syntax. Yeah. Hello world. And all it did was take the value, here it's the string hello world, and it printed it out. It displayed it to the screen. That's it. It's simple, but it's a program. We told the computer to do it, and it did it. Great. So who here did this already? Great, you're a programmer. If you've never programmed before, well, you just did. It's a program. I'm not being silly. It's a simple program, but it's a program. So there we go. Any questions about this at this stage? Now, like we talked about briefly last time, someone pointed it out, I'm going to, if you have not already, I'm going to highly suggest you go to Settings, Editor, Show Line Numbers. I know I said it last time, but it always gets somebody where they get confused and they start writing. If it doesn't show the line numbers, they start adding them in, and we don't want that. The line numbers are just there for us to see. Hit Run, hello world, we're good to go. Cool. Next, okay. So, you know, what's a computer? Or what's computation? You know, I know you've heard the word computation before, right? You may have even used it. But have you ever really thought, wait, what the hell does that word actually mean? You know, it's something to do with computers, right? But what is computation? Can anyone tell me? I'll get a chair and get comfortable until we get participation. Well, they hit all the chairs. But who can tell me what computation is? Say that again?
Thinking with the intent of problem solving.
Thinking with the intent of problem solving. That's not too bad. Any other ideas what it means? Like I said last time, raise your hand if you were in high school last year. Yeah, apathy isn't cool anymore. It never really was, you just thought it was. So let's try this again. I can lecture at you like every other prof you're going to have lectures at you, and you're not going to like it. So let's try again. Who can tell me what computation is? Or at least try to tell me what computation is. I know you've heard the word, so what does it mean? Say that again? The use of computers. Yeah, but like computers do computation, right? So like what do you think?
Just like acting out or solving a certain math question, mathematical
Yeah, that's kind of like his answer, but a little bit more specific, so that's good. What were you going to say?
I was just going to say problem solving.
Problem solving, yeah. I mean, we all kind of know what this word means, yet when we think about what it means, it's kind of hard to go, well, it's that. I mean, really, it's like this process of taking steps and doing some calculations, maybe taking some input, doing some output, changing states. It's kind of like what computation is. But, what's a computer? Someone point at a computer. Everyone point at a computer. Can anyone point to a different type of computer? I see what you're pointing at, yeah. Can anyone point to another computer? Your phone. Anything else? You're pointing at your head? Why are you pointing at your head?
I feel like computers and brains kind of do similar things.
Not only do they do similar things, they literally do computation. Computers, I mean, in today's world, when we say computer, we all know that we mean this. But when you look at what the word computer means, it doesn't mean that. A computer is anything that does computation, anything that can take input, perform some computation, perform some calculation, change states, maybe produce output, just do something. Your brain is absolutely a computer, and I'm not being silly. You talk to neuroscientists, and some of them start getting whiny about semantics of what it means, but there's no ifs, ands, or buts. It is definitively a computer. Something as simple as a lock is a computer. A key lock. Maybe like a safe code where you hit buttons. It's a computer. It's a very simple one. But it could take input, change states, and if the input's right, it produces some function. It unlocks. If it's not, it doesn't. It's a computer. And I'm not being silly. I'm not stretching the limits of what the word means. No, it absolutely is. It's a very simple computer, but it is a computer. Computers are everywhere. You figure there's cells in your body doing a shit ton of stuff all the time. They're performing function. They're performing computations to keep you alive, keep you doing what you're doing. Have you ever sorted, raise your hand if you've ever sorted anything in your life. If you don't raise your hand, you're asleep. Wake up. Of course you have. Of course you have. How about search through a pile of things for something? You ever do that? That is a task that you solved through computation. Sorting is actually kind of complicated, right? You got to find things and put them in order. It doesn't seem complicated, but it kind of is. It's a complex problem. But if you did it, that's performing a computation, and you're a computer. Okay, talk amongst yourselves. I'll give you 3 minutes, 2-3 minutes to do this. And okay, raise your hand if you ate breakfast today. Raise your hand if you would have if you had a little bit more time. Okay, there. At the very least, explain to somebody else around you how you did or how you would make breakfast in the morning, step by step, such that they could recreate it. You throw them in your house, in your kitchen, they don't know what it looks like. Explain to them how to do it. Go, do it. All right, it's getting kind of quiet, so I'm going to guess maybe you're done. Who's going to tell me how they made breakfast this morning? I'm you. I'm in your kitchen. Tell me how to make breakfast this morning. I need a volunteer. If not, I'm going to point. All right, tell me what to do. I'm in your kitchen.
I opened up my fridge.
Well, hold on. Where's your fridge?
On the floor.
On the floor. All right.
It's like standing up though.
Okay, but where is it? Over here, over there, right in front of me?
My room, corner of my room.
Pardon?
The corner of my room.
Okay, where is that? Is it in front of me? Is it over there?
Over there, I guess.
Okay, give me the steps to get there.
Walk over there.
Over where? Maybe you should tell me to turn right or left or something.
Turn left.
Okay. Did you mean that way?
No,
All right, yeah.
walk forward a few steps.
How many?
3.
About 3, you think? Yeah. Okay. 1, 2, 3. Is that good?
Yeah.
Pretty good. Yeah. All right.
Reach slightly forward.
Like this way?
Yeah.
All right.
Grab on. Pull
Pull. Which way? This way or that way?
toward you.
I don't want the fridge to fall on me. Does the door open this way or that way?
Like something like this.
All right.
Reach in.
Well, hold on.
Reach it with the other hand.
All right.
Grab the protein shake.
Well, okay. Where is it? Did you make the shake the night before?
Pre-made.
Pre-made shake. Okay.
It's on the side door.
Oh, okay. So like over here?
Yeah.
Or is it on this door?
No, it's on the side door.
All right. All right. Where is it?
On the side door.
Yeah, but like there's like 3 shelves, right?
Yeah, it's on the top one.
It's on the top one. Okay. Here. What do I do about it?
Lift it up.
Lift it up. Wait, lift what? The protein shake? I mean, my hand's down here. I mean, you were telling me to go around. Where do I put this hand?
What?
Where do I put this hand?
Where the protein shake is.
Which is where?
In the fridge door.
In the fridge door, right, the top shelf. Okay, yeah.
Yeah, and then take that. You can close the fridge now.
Well, I should probably move this hand, right?
Yeah, maybe.
Okay, I'll move it. And now close the door, yeah.
Then with the other hand, twist off the cap of the protein shake.
All right, yeah.
And then you can drink it.
How do I do that?
Lower your hand towards your mouth. Other hand.
Oh, right.
And then drink it by like tilting your head back. Yeah.
Okay, good, there. All right, there. I got it. I just ate breakfast. Now, I was being kind of nasty, right? I was being kind of silly and trying to get you to be more and more specific. But I mean, if you're talking to another human, you could usually be like, okay, go to the fridge. They could locate the fridge. Open the door and look in the door for the shake. They just grab it, right? But that's describing the steps at a very high level. We would call that a high level of abstraction. And I could play that game of being more and more and more and more and more specific forever. I could go all the way down to subatomic particles. I didn't go that bad. I was like, okay, tell me where to move my hand. But I could play that game, and that's a much more low level of description. So there's different levels that we might need to have to describe steps of instructions for something to perform those steps. Sometimes we can get away with, you make pasta by boiling water and throwing it in and waiting 9 minutes. Or you have to say, locate the pot, grab the pot, walk it to the sink, you know. Those are 2 very different levels of detail. But what we just discussed there, the steps of making breakfast, although you didn't really make breakfast, you just grabbed it. But the steps of having breakfast, that series of instructions, that formally we would call an algorithm. Have you ever made a cake or baked cookies or followed a recipe ever in your life? Raise your hand. Of course you have. That recipe, it's an algorithm. That's the mathematical term for that. Raise your hand if you drove to the university today. The steps you took to get here, that was following a series of instructions that, I mean, you knew the instructions, but you followed those instructions to do something, and you got here. Your instructions were right, because if they weren't, you wouldn't be here. That's an algorithm. It is. Program. You know, you could use those words kind of like interchangeably. So that's an algorithm. That's it. A series of instructions, a series of steps that we follow to do something. What is debugging? Well, like I was saying last time, debugging is basically what programming is. Fixing mistakes. Remember, you're going to be wrong every time before you're right. Most of your code's going to be wrong, and this is going to be true whether or not this is your first program you ever wrote, or if you're a 30-year veteran programmer. The code you're going to write is going to be wrong. It's not because you're new that you're wrong. It's because you're programming. That's why you're wrong. Because that's what programming is, being wrong all the time until you're right. All you get when you get more experience programming is you know how to avoid certain bugs, but other bugs sneak up on you. More complex bugs, maybe. Maybe you go a little bit longer before encountering a bug, but you're hitting those bugs. Debugging is the process of addressing the bugs in your code. Some bugs are easy to find. Some of them are like the error message we just saw when I did print wrong, right? It said syntax error. If I go here and delete this parenthesis, it's going to say, yeah, incomplete input. That's a bug. And that one's kind of easy to fix in the sense that it showed me where the issue was. Some bugs, not so much. Some bugs are a little quieter, where it seems like everything worked, but something didn't quite go right. Either way, they're all bugs. And get used to dealing with them because, again, that's what you're going to be. And the reason I'm emphasizing this so much is because, I know I said this last time, but new programmers, when they don't have the expectation, like you might not really understand when I'm saying you're going to be wrong all the time. I don't mean like, yeah, it's going to be a struggle. I mean, no, you're going to be wrong a lot. You will be working on the assignment for, let's say, 8 hours. For 7 hours and 55 minutes of it, it's going to be wrong and you're going to be fixing it. But for 5 minutes, you will have done things right. Not all at the end, interspersed. Maybe you go an hour and a half and you get something right. You go 20 minutes, you get something right. And so on. You're going to be wrong a lot. That is the process. That's not because you're bad, that's because you're programming. Sure, you're still learning, and that's going to cause some of the issues, but that's programming. So when you're new at this, and it's been 2 hours, and you're like, oh, the person over there got it done, I must be bad at this. No, you're remarkably normal. That person's the weird one. What did they do to get it right? Be suspicious. Be wrong and expect it. You're going to be wrong. You're going to hit run. Sometimes to get something working, you got to hit run 72 times. So you're going to hit run 71 times, it's going to be wrong, but maybe that 72nd time, it's right. The point is, you were right once out of 72. That's going to happen all the time. Have you seen any Python errors yet? I mean, we just saw one. What were they? Did you understand them? Sometimes the errors in Python, like I was saying, is kind of easy. Incomplete input. It's even got little arrows saying like, yeah, okay, it's pointing to where the issue is. Okay, yeah, close the parenthesis. Maybe I do this. I misspell print. It's going to say name print is not defined. What? Oh yeah, because it's not print, you know. It's telling you where the issue is. So sometimes Python's really good at being like, here's your problem. Sometimes it does its best at telling you where the problem is. Sometimes it's not that clear. And sometimes, like I was saying a moment ago, it's going to look like everything was fine, but it wasn't. And those errors are tricky. Those errors can be catastrophic and deadly, like literally deadly. When everything seems to be working, but in funny little cases, something goes wrong. Nothing we do is going to be deadly, though. Don't worry. Okay, languages. Who here knows how to speak English? Right? Okay, great. That's a natural language. That's a language that, it just kind of happened. We just started speaking it one day, and we were happy, and we were good to go. Right? It evolved to what it is today. And it evolves every day that goes by. The way we talk today is a little different than the way we talked 10 years ago even, right? Like our slang changes, just how we communicate, it changes. The formalness of it, it changes. But the point is that's a natural language. We all kind of understand it. And the funny thing about natural language is it's actually like, it's a little different today, but if this was a year ago, it's a little easier to say, natural languages, they're hard for It's hard to sit down and come up with all the rules of English. You can go look at them, and there's rules, and then there's more exceptions to a rule, right? It's weird, yet somehow we all understand it. There's literally a chunk of our brain responsible for language. Thank God it's there, because otherwise we'd be in big trouble, right? Because English is far too complex. Every natural language is really complex. Formal languages, on the other hand, like Python, we call that a formal language. It's not like a natural language, and it has rules. It's very strict about its rules, which makes it simpler. Now, simple doesn't mean trivial. It doesn't mean you're going to understand it like that. But it's simpler in the rules around the language versus something like English. English, you just intuitively know all the funny little quirks of English that you just know how to speak it, right? Formal languages, there's no like funny rules that you just have to know. I mean, there are, but there are a there's a rule book you could go look up. And the rules are the rules, and that's the rules. English is, those are the rules that we follow 10% of the time. The rest of the time, we just say whatever the hell we want, and people get it. Because, you know, with natural language, the point of natural language is I have some information in my brain. I want to make it get into your brain. So I do that by making sounds with my face, and you listen with your ears, and it gets into your brain, right? The point is communicating. The same idea with the formal language. We're communicating stuff, but we have to be very precise and very specific, because with natural language, there's a lot of flexibility. You know, you read a book, you read a poem, people get really fancy with their prose. People get really fancy with how they communicate, where it's not just what they're saying, but it's how they're saying it. There's rhetoric involved. There's a lot going on with a natural language. Formal languages do not like that crap. Consider, for example, the statement. Pay attention, because some people get this immediately, and some people don't quite wrap their head around why this is funny. Consider the phrase, "This statement is false." This statement is false. Great. You know, we could read that. Individuals who know the natural language English, we can read that and be like, okay, this statement is false. Okay. But imagine telling like a computer that and trying for the computer to try to understand what that is saying. What is that piece of information? I want to read that and know what that means. If I read the statement, "The car is green," and you told the computer that in a formal language, it's going to say, okay, that car, it has like the property of being green. Okay, cool, got it. This statement is false. Okay, what does that mean? If that let's parse what that means. This statement is false. So someone tell me superficially, what does that mean? It means it's not right. Meaning whatever information is in that statement, I shouldn't trust it, right? Whatever that statement is telling me, I shouldn't listen to it, because the statement's telling me it's false. Meaning, if the statement is then telling me it's false, and I shouldn't trust it, what should that statement actually be saying? That is true, right? So if this statement is false, that means I shouldn't trust it. It's telling me, like, don't trust me. I'm false. I'm wrong. So if it's wrong, what's the opposite of false? True. So if it's true, then I should listen to what it says. So it's telling me it's false, meaning whatever it's saying, do the opposite. So it's false. And if I'm doing the opposite, that means it's true. So if I do what it's telling me to do, I should believe what it's saying. And what is it saying? Well, it's telling me that it's false. But if it's false, then I shouldn't listen to it, which means it's true, which means I should listen to it. And then if I'm listening to it, it's telling me that it's false, which that means I then shouldn't listen to it, which then makes me conclude that if it's not false, it must be true, which then means it's false. And do we see a problem here? Who here knows who Pinocchio is? You know, the little wooden boy. What happens to Pinocchio when he tells a lie? His nose grows. So imagine there's Pinocchio sitting right there. Right? Here's Pinocchio right here. He's a little wooden boy. And he says to you, listen very carefully. He says to you, my nose is going to grow right now. Okay? And we're sitting and we're waiting to see what happens. What should happen? Someone tell me what should happen when Pinocchio says, my nose is going to grow right now. Who's brave enough to explain what's going to happen?
Okay, so the fact that he's saying that if it doesn't happen, then it's a lie, so it will happen. But if it will happen, then he's telling the truth, which means it shouldn't happen.
And that, but then Pinocchio should never say that statement.
Yeah.
What were you going to say?
Would being wrong constitute as a lie, though? If he says that it
Well, he's asserting it's going to grow, right? Let's make it clear, like he's asserting it's about to grow. If he was, I know what you mean, right? Like, well, was he intending to be wrong? Let's assume what he's asserting is tied to his intent, for the sake of argument. But good point. So let's be clear. Pinocchio's sitting down right there. He says, my nose is going to grow. If he's sitting there and his nose does not grow, he just lied. He said his nose was going to grow and it didn't. And if he lies, what happens? His nose grows. But then his nose would have grown. Meaning, man, what were you going to say?
I was just going to say, like, if he said it with, like, the intent of, like, lying, without even realizing that it was actually going to happen, then, like, wouldn't it still count as, like, a lie?
Well, that's what he was saying, right? So let's assume for the sake of argument, he may or may not, like, he is either intending to be telling the truth or intending to lie. Assume the assertion, my nose is going to grow now, is he's aware that his assertion, if he's wrong, he's lying. It's not like I was wrong, oops, I made a mistake. It was, no, I was lying. Let's assume for the sake of this argument. So he's sitting there and his nose does grow. He told me, because there's two options. He sits there and his nose doesn't grow. If his nose doesn't grow, but he said it was, that means he's lying, which means it grows. But he just said that his nose is going to grow, and so if it didn't grow, that means he was lying, therefore it would grow. Which means he wasn't lying, which means it should never have grown in the first place. Let's flip it. Let's go the other way. He's sitting there and his nose does grow. He sits there and says, my nose is going to grow now. And it does grow. His nose only grows when he's lying. But if he just sat there and said, my nose is going to grow now, and it grew, it means he was lying. But he couldn't have been lying because he just said his nose is going to grow, which means it shouldn't have grown if he wasn't lying. But then if it didn't grow, he would have been lying, meaning it should have grown. We're stuck in this loop. Yeah. Well, let's not focus on these details, because we can play this. He could be like, my nose is going to grow right now. I'm made of cheese, right? And no one hears it, then it grows, and suddenly, that's the only way Pinocchio can get away with it. Otherwise, like I said, Pinocchio should never say that statement, because no matter what happens, it's not going to be good for him. I don't want to know what happens to Pinocchio. Someone in the other section, it makes him a real boy, which I thought was pretty funny. All right. The point of that is, for us, we can have fun with the statement, this statement is false. But when the computer is trying to understand what that means, like in a formal language, we can't have things like that. It's going to be like, no, that's not, there's nothing to actually understand there. There's nothing to properly compute. I can't compute what that means. Okay, some terminology I'm just going to throw at you. You may be aware of this, you may not. Most of this I'm not actually going to be using throughout the semester, but it might pop up here and there, so I'll just say it. Hardware, software. Hardware, that's like the physical things, like your actual physical computer, your physical keyboard, your mouse. Software, that's like the programs running on your computer, right? It's Microsoft Word, it's your browser. Input, output. Input is putting input into the computer, putting data in. Output is getting data out. Input would be like typing things into the computer. Output is displaying something, like print actually did some output. Processors, a processor, you've all at least heard the word processor before, right? Your computers have processors. A processor, that's the actual thing in your computer doing all the number crunching, for the most part. It's the thing where all the instructions and data goes, and it does all the calculations for you. Storage, like hard disk or solid state, that is long-term storage. That is where all of the information, like raise your hand if you've got a video game on your computer right now, right? And that video game's pretty big. A couple of gigs, maybe like 100 gigs, I don't know. That's got to be stored somewhere. Those zeros and ones that mean that game has to be like literally physically stored somewhere, and it's put into that long-term storage, your hard drive, solid state drive, whatever it is. And then you have memory. That's another form of storage, but memory is more like a working memory. Memory is where information is stored that's being actively used. We could start to get more precise with things like registers and cache, but we're not going to worry about that right now. So to draw a comparison, if I'm making a cake, my long-term storage, my hard drive, is like my fridge and my pantry. Memory is like what's on my countertop. Like I brought all the ingredients out that I need, so they're at hand. And the processor is me, making the cake, right? Mixing things together. Binary, raise your hand if you've heard the word binary before. It just means it's a different number system. Instead of counting from 0 to 9, we count from 0 to 1 and then go back to, so go 0, 1, 1, 0, 1, 1, 1, 0, 0. It follows the same rules as a decimal system where you've got, 10 symbols, except we only have 2. We'll talk maybe a little bit more about that later. Compiling, when you write code on your computer, your processor, it doesn't care at all about the code. It doesn't understand the code. It only understands really low voltages and high voltages, right? When you have low voltages going through all the circuitry and high voltages, that's how all the calculations get done. So compiling is the process of taking your code and turning it into something that your processor would be happy with. And then there's also like interpreter and like bytecode and whatnot, which is starting to get into the weeds of very specific types of things, but let's not worry too much about it. So there's some words there that you might hear. Now print. Back to print. So, okay, any questions so far about anything we talked about before I go back to talking about specific code stuff? Yeah?
So this statement is a lie, paradox kind of thing, that would make your computer blow up?
Well, no, it wouldn't blow up. Well, okay, it could mean different things in different contexts, but the point here is that, so the point here is, one of the biggest discoveries of the last century, there's two sides of the same thing. There's the math side and the computer science side. Who here has heard the name Alan Turing before? Yeah, he's a pretty big deal. He basically invented computer science. It always kind of existed, but he was the one that was like, wait a minute, this is a thing. One of the discoveries he made was, well, can we build a computer to compute everything, like anything and everything? Is it possible? And up until not that long ago, everyone's like, yeah, sure, why not? Now, not in the computer side, that was more the math side. The math side was more about can we prove everything within our system? Within our system of mathematics, can we prove and understand everything? That's what we hope is true. And for a long time, that's what everyone assumed. But then some important people came along and kind of figured out and proved that, oh shit, we can't. We actually know that there are things we can't know. But the worst part is we don't know what things we can and can't know. We just know that, like, if there's a problem in mathematics, right? And we're like, oh, it's still not solved. We want to solve this. This discovery in the last century tells us that that thing you're trying to solve might not actually be solvable. We don't know if that thing's not solvable. It might be, it might not be, but you might be wasting your time. We don't know. So the computer science side of it was there are some things that are just not computable. For example, that is an example of like this paradox of like, well, you know, there's a little bit more sophistication to it, but that is like a simple way to describe it. Fantastic question. Other questions? Okay, so print. We already did print. Because I've been talking a while, if you haven't already, go to Colab, run print again, but put in a string of whatever you want. Try to come up with the most inappropriate statement you can print out for the fun of it. I don't care. Do whatever you want. If you've got your computer, make it print out whatever the hell you want. I'll give you a minute to do that. Okay, raise your hand if you're done. Raise your hand if you'll be done in like 10 more seconds. Okay, I'll give you 10 seconds. Did anyone not get it working? Because if you didn't, let me know, and I kind of want to see what bug you hit. Because if you hit a bug, that's actually something I really want to emphasize. If at any point, and this isn't just for this course, this is just advice for university classes in general, for those of you that's new to this. If you've got a question about something, if something's unclear to you, but you're thinking to yourself, I don't want to ask it, maybe I'll look dumb, maybe it's not that important, I don't know. If you're thinking that, chances are at least half a dozen other people in the room are thinking the exact same thing. But you're all playing a game of chicken of hopefully someone else asks. I don't want to ask. Just do everyone a favor and just ask. If you've got a question, ask. And half the people in the room are going to be relieved that someone asked that question. So yeah, if anyone here get a bug that it just didn't work for some reason? No? Well, that's good, but if you did, you know, it'd be good to say something so we can see and maybe we can figure it out. All right. So print. Print is a function. Who here has heard the word function before? Probably in the context of like math class, right? F of x. F of x equals x plus 1. That's a function. That's a math function. It's the same idea with programs. There's a function defined, and the function has some operation it does. And the f of x equals x plus 1, well, it just adds 1 to whatever x is. So if I said f of 5, what happens? Well, you get 6 back, right? Well, this is print. It's a function. You give it a value, and then it displays it to a screen. That's its function. Consider for a moment that that function, it must actually be doing a lot under the hood. Go back to that a moment ago when I was having you describe how you got your shake in the morning, right? I played that game of, let's see how low level I could go. How dumbed down could I make it where it's like move, arm, lift, up, open, right? As opposed to go to the fridge and grab the shake. This print function is more analogous to go to the fridge and grab a shake. It does a lot for you. It prints to the screen. It takes the value, it figures out what pixels need to actually be turned on and whatnot. There's a lot going on under the hood. If you look under the hood, you break that function down into like, well, what's it actually doing? It's going to look a lot more like, okay, move arm, open, grab, hold, and whatnot. But print, there, you get it for free. It's a function somebody wrote for you that you get to use. That means display this to the screen. Thank God it exists. And I'll tell you right now, print is a damn handy function, not for just printing things out, but often when programming, you're going to have variables and whatnot, which we're going to learn about. And if you're ever lost going like, when I did x plus 7, I was expecting to get the number 11, but I got the number 17. That doesn't make any sense. Why? Why? Well, maybe I should print out the value of x. Clearly, I was expecting x to be 4. But when I did x plus 7, I got 17 or something. Whatever I said. Meaning x must not have been. Let's make sure x is 4. Let's print out x and see. That type of thing, right? You're going to be writing prints a lot because it's great for easy debugging. Okay. Values and types. So, values is like the data in the programs that's being worked on, being manipulated, stuff's happening with the data. We saw strings. That's like the words, A, B, C, D, E, F, G, or hello world. You could take the whole contents of your favorite book, put it into one big string, whatever. Whenever I say string, I mean words. I'm going to use the word string from now on. Strings. They're called strings because it's a string of characters. Okay? There's integers, 7, 42, 97. And then there's also floating point numbers. That's a fancy word for it's a number with decimals. There is a difference between numbers and like just whole numbers and numbers with decimals as far as the computer's concerned. And notice for a moment that beside each of these values, I specified that they had a type associated with it. There are strings, there are integers, and there are floating point numbers. There's more types as well, and we can even make our own types. But those are types, and they all have a different set of values that are allowed. Strings can be literally any combination of strings, of letters and characters and whatnot put together. Integers can be any integer. Floating point numbers can be any floating point number. There's a million asterisks associated with that, but we'll talk about that later. Whenever you see a value, like the values described there, like the string A, B, C, D, E, F, G, or hello world, 7, 3.792, whenever you see a value written like at face value, we call those literals. This is a word that you don't really hear very often, but they're called literals. The number 3.792 is literally the number 3.792. This is as opposed to variables, which we'll talk about in a moment if we actually get there today. Okay, string, integers, floats. So to a computer, the integer 1, the value 1, that's an integer, and the value of the string 1 are entirely different. Let me show you what I mean. Print 1 plus 1. What do you think is going to happen when I hit run? Someone take a wild guess. You don't have to be a genius to figure this one out. Yell it out. Is it going to print 2 plus 1 or 2? It printed out 2. Why? Because it saw the integers 1, and when it sees plus next to integers, it means we'll add them together. I could have made this a string, and now it prints out the string 1 space plus space 1. I can add the integer 1 and the floating point number 1. It's the floating point number because it's 1.0. Even though the integer 1 and the floating point number 1.0 has like the same like intrinsic value. They are different as far as the computer's concerned, but the computer's happy to add them together. But what do you think is going to happen? Let's go back here. If I try to add the string 1 and the integer 1, what does that mean? What should happen when I add the string 1 and the integer 1 together? What should I get? Come on, it's an easy question, right? Or are you going, that's not a thing. You can't do that. What does that even mean? Well, Python agrees with you. It's going, that's not a thing. I can't do that. And if you're asking, well, why is that a bug? It's because, well, you tell me what it should have done. What should happen when you add a string and an integer together? Do you know? I don't know. Seems like a stupid question to begin with. And that's what Python told you. That was stupid. I can't do that. Now, here's something funny. You may or may not know the answer, but I want someone to guess. What do you think is going to happen when I do this? The string 1 plus the string 1. Well, tell me what you were going to say. It adds them together. But what do you mean? Okay, yes.
Not like adding like 1 plus 1, like it takes the 2 and
It smushes them? Yeah. Concatenates them? Let's see. Oh my God, there you go. Do you remember as a kid, you'd be like, what's 1 plus 1? Your friend would be like 2, you'd be like, no, it's 11. That's what Python just did to you. The string 1 plus the string 1 comes together to mean 11. Let me put it like this way. A, B, C, D. What is the string AB plus the string CD? It's A, B, C, D. So for Python, when you do plus on strings, it means concatenate them. When you do plus on like numbers, it means, well, addition. So plus can mean different things depending on the type of the operands. Remember being this big, just one sec. Remember being this big and hearing the word operator and operand? Who here remembers the difference? Who here at least remembers hearing those words? Give me a break. Come on. All right. So the reality is you would have heard these words when you were like this big, and then you probably never used them again ever. Well, I'm bringing them back. Operator is like the plus. Operand is the things that the operator is being applied to. So the type of the operands can impact what the operator actually does. What were you going to ask?
How does using a minus or multiplication work?
Very good question. What do you think is going to happen? It doesn't know. Now, here's a weird one, though. Watch this. What do you think is going to happen if I do AB times 5? AB, 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 AB. So there you go. So some of them are defined, some of them aren't. And the best way to learn it is to just try and see what happens. I wonder what's going to happen if I do divided by. Yeah, I didn't think it would work. I legit was like, yeah, I don't think it works, but no, let me see. Yeah. All right, we'll end here for now. Any last questions? Yeah. Try it, and you let me know.